Good evening. I'm Jim Kakalios, the head of the School of Physics and Astronomy. I want to thank you all, first of all, for coming out on a rainy Tuesday to hear a talk about quantum mechanics. My kind of people, nerds. How many people saw one of the Summer of Astounding Astrophysics talks last year? Okay, some, but not everyone. Great, awesome. That was the first time we decided to try that, and the response was very positive. We decided to try to get a bigger room, and other faculty said, hey, okay, we don't do astrophysics, but and so we broadened it out. And so I welcome you to our summer of Quirky Quantum Physics. I guarantee you that if we continue this, it's always going to be an alliterative name. So what you'll see this summer, every Tuesday, 7 o'clock, in this room, no registration required, no tickets. Next week, there will be a talk by Professor Martin Grevin about superconductors. Professor Fiona Burnell will talk about quantum computing and what the whole deal with quantum computers is. No math in any of these talks, by the way. We got somebody talking about quantum tunneling, a tunnel through nothing. They asked me, what are you an expert in? I said, nothing. They said, oh, we got a job for you. Professor Alexei Cherman will talk about why particles don't exist. Again, quantum field theory with no math. And the last talk will be by Professor Michel Janssen, who is in our physics department, but he's a historian of physics. This year, he won the highest prize that the American Physical Society gives to people who do the history of physics on the foundations of quantum mechanics. And so he has a great talk on how it began, basically the first 25 years. So this should be a lot of fun. But before we get to the fun, my talk. So I want to talk about solid-state physics. Quantum mechanics has a reputation for being very confusing and very abstract, and it is. But one of the most amazing things about it is that you can use it correctly and productively, even if you're confused by it. And the people who are using it, physicists and engineers, are confused by it. And yet, the world we live in relies on it. Here we are, it's 2026, we're well into the 21st century, and this is not the world of tomorrow that we were promised. We were promised jetpacks and flying cars. And what we got instead were smartphones and laptop computers. Now, these devices seem like magic. But by the end of this talk, I hope to convince you that it really is magic. Now, I don't mean magic like Marvel Comics' Doctor Strange and the all-seeing eye of Agamotto, but rather magic like Harry Houdini or Penn and Teller. They don't break the laws of physics, they exploit the laws of physics in order to create amazing effects. And we do the same thing in quantum mechanics. A little interesting historical coincidence, the very first science fiction pulp magazine that would publish the very first stories about Buck Rogers was Amazing Stories, created by Hugo Gernsback. First issue came out April 1926. Also publishing in January 1926, Erwin Schrödinger, who published the Schrödinger equation. So these two visions of the future start different parts of the world, but at nearly the exact same moment in time. One that would lead to lasers, and the other that would lead to death rays. Now, Schrödinger, this is the Schrödinger equation that he thought of, and it basically says, you tell me the forces acting on a system, and that goes into this letter V that's here, and I will turn a crank and I will solve for this Greek letter psi. And by doing mathematical operations to psi, it will tell me what the system of the atoms, light, whatever it is, are doing. He developed this 1926 because he and a handful of other scientists were trying to understand how atoms behaved and how they interacted with light. Pure curiosity-driven research. A generation later, scientists, engineers at Bell Labs developed the transistor, and separately another group developed the laser. A generation later still, you get cell phones, laptop computers, magnetic resonance imaging, all things that I'm sure you would agree, without which life is not worth living. If you went to Schrodinger in 1926 and said, "Nice equation, Irwin, what's it good for?" I doubt he would say, "Well, if you want to store music in a compact digital format." But without this foundation, the world we live in would look very different. Okay? So, I'm going to, by the end of this talk, tell you about how transistors work, solar cells, lasers, and give you a foundation of really why they work, and touch on at the very end some nanotechnology. So first I have to teach you quantum mechanics. And I have 10 minutes, which leaves me with a problem. What am I going to do with the other 8? Because this is an audience that can understand quantum mechanics like that. There's basically, now, don't tell Michel Janssen that I said this, because he gets like really upset when I summarize quantum mechanics this way. By the way, not once, except for just right this now, will I ever say the words Schrodinger's cat. We don't need to know. There's no mystic mumbo jumbo, just 3 impossible things that you have to accept. One is that light has both a wave and particle-like nature. That is why we refer to light as photons. The other thing is that matter also has a wave and particle-like nature, and that everything, light and matter, has an intrinsic rotation, a spin, like spinning like a top, right? Why? Take it up with the boss. It was like that when we got here. Okay? Now, when I say light has a particle-like nature, what do I mean? There was an experiment that was done where people shined light onto a metal, and they saw electrons come spitting out of the metal. And they were trying to understand, why is this happening? And if light is a wave, you can think about like the ocean waves crashing on the beach. And if the waves are particularly large amplitude and really energetic, they might hit a pebble and move it further up the beach. And as the waves keep coming in, they might push the pebbles up to the boardwalk. And if they reach the boardwalk, we'll say they shoot out of the metal. So the thing that matters is how high the waves are. It doesn't really matter the spacing between the waves, what the frequency, but that's not what's seen at all. You could have a wave that's like a tsunami, but if there was a really large spacing between the waves, no electrons come out. You could have a very low amplitude wave, but if the spacing between the waves is small, a small wavelength, or another way of saying it, the frequency, then the electrons come out right away. This is called the photoelectric effect. Physics at the time couldn't understand it. In 1905, this one guy that no one has ever heard of came up with an explanation, arguing that the light was actually these bundles of energy that were later on called photons. The energy of the photon is a constant, which is Planck's constant, times the frequency of the light. This guy, by the way, Albert Einstein, did this in 1905. This is what he got the Nobel Prize for. Not relativity, not E equals mc squared. By the way, 1905, he also wrote a paper on relativity. He wrote a paper on E equals mc squared. He wrote 2 papers about statistical mechanics that if he did nothing else, physicists would know him for. He did this all in 1 year. This is what we call in physics having hot hands. Keep your eyes on this kid. I think he's going places. Anyway, so this is an example of light acting like a particle. photons. And of course, we know there's a lot of practical applications to light behaving like a photon, like a particle. So we can just work on that. Okay, matter has both a particle and wave-like properties. What does that mean? What is the wave? When you say what is characteristic of a wave that is different than anything else, one of the arguments would be that it can interfere. That if you have a wave, say I have a wave, a light wave, and it's bouncing off a surface, or it goes through a material, bounces off another surface, and comes out. Now, if the thickness of this little slab here is the right ratio of the wavelengths of the light, then when these two waves come out, the two peaks are at the same point, the two minima are at the same point, you add them together, you get a bigger wave than you had before. Constructive interference. Or, if the thickness of the slab is just a little bit different, you could have a peak of the wave correspond to a minimum of the wave. And so you have a large piece and a small piece, you add them together, you get 0. By the way, these are how the noise-canceling headphones you have work. It detects the background signal, the background noise, does an analysis of it to see what are the wavelengths, creates a wave exactly the same, but flipped 180 degrees, and the two waves add together and cancel out, and that's a noise-canceling headphones. We see this, in fact, we will definitely see this today if there's any oil on the sidewalk or on the street, because on the wet sidewalk, the wet street, the oil is repelled, so you'll have a little thin slab of oil. And when you see a spectrum of light, it's because the white light is coming in, and at certain points in the oil slick, it has a thickness such that certain colors constructively interfere. So these patterns that we see are hallmarks of wave-like phenomena. Okay? If I take a laser and I shine it on a grid, I can see these amazing patterns, speckle patterns. And again, this is just simply constructive interference, constructive and destructive interference of the light. Or I can take electrons and bounce them off a surface of a crystal. Whoa, what happened there? Oops. Huh. There. I can take electrons and bounce them off the surface of a crystal, and every time they bounce off an atom, they can reflect. And there's a relationship between the wavelength of the matter wave and the momentum, which is mass times velocity, which is related to the energy of the electron. And that has to, again, Planck's constant shows up again. And you can get constructive or destructive interference of electrons. Not of light, but of electrons. And this was the pattern for lasers. This is a pattern, kind of hard to see here, but you're seeing the same rings, the same dots around this. If there are better images, this is a little bit too bright in here right now, but I don't want to dim the lights just for this. But this is the same type of a pattern, but for electrons off of a graphite crystal rather than laser light off of a grid. And that everything, light and matter, has an intrinsic spin. Okay? What I mean by that is the spin, like say a figure skater or a ballerina doing a pirouette. All matter is spinning as if there is an axis that's going through it and is rotating. And one manifestation of this rotation is that it creates a magnetic field. Electrons have mass, they have charge, they have magnetic fields. Protons, neutrons, all matter, photons have not a magnetic field, but they have a rotation, a degree of rotation as they're moving as photons. Again, who ordered this? This is just the way it was. With this magnetic field, and if you're rotating about an axis through the sphere, there's basically only two ways you can rotate, clockwise or counterclockwise. So you either get a magnetic field pointing in one direction or another direction. This will be important later on. This, by the way, this is true of the electrons, it's true of the protons and neutrons in every atom in your body, And this is the basis of magnetic resonance imaging. You have the nuclei of the atoms in your body having a magnetic field. You lay down on the table in a much larger magnetic field, and then they vary they do a small variation of the magnetic field. They send radio waves in. Radio waves are great because they penetrate through your body, right? You can always get a cell phone signal even if you're holding the phone behind your back, right? Or if you're sitting on the phone, in which case you can not only get a call, but you can dial. But this is the basis of this. Again, when they were discovering this, they were just trying to understand the intrinsic magnetic fields that were present in nuclei, never thinking that this would be the basis of this technology that I've read the old science fiction pulp magazines. Nobody predicted MRI. Nobody thought that there would be a device that you could be awake, lying in, talking to someone, and they could see an image inside of you without the cut of a knife. Okay? I have a friend here at the university who works in the magnetic resonance lab, Bruce Hammer, and as a favor, he took some photos. He did an MRI image. Does anyone know what this is? Yeah? These are Reese's peanut butter cups, that's right. Because you could verify that there's peanut butter inside by biting into it, but why would you do that when you have an MRI machine that's sitting right there that can image the peanut butter inside the chocolate cup? By the way, I get that spot checked out. Anyway, okay, so that's all you need. That's all you need to understand the rest of this talk, to understand solid-state semiconductor physics. Coming up. Okay, so how do I combine these three? Matter has a wave-like properties, and it's associated with the momentum. It associates with its motion. One of the key things will be what's called standing waves. We're all familiar with standing waves. A violin, a guitar string is clamped at both ends. You pluck it, and you can only get certain vibrations, certain wavelengths, right? And that's required by the fact that at the two clamped ends, the amplitude has to be 0. Otherwise, it's not a standing wave. This would be a standing wave. This would not be a standing wave. This is something that's just clamped at one end and is then moving up and down. Okay, what if I take that string and instead of having it clamped at both ends, just bend it around into a ring? If it's a standing wave, that means that any given period to go around, when I get back to where I started, I better have exactly the same wave. Because if one's high and one's low, that doesn't make any sense. So that means that only certain wavelengths could form orbits around a nucleus for the electrons. And since the wavelength is related to the momentum, which is related to the energy, that means that only certain energies. We actually can see this. We have a demo that we do in the physics class of this is a ring that's on actually it's just an audio speaker that's vibrating, and we can change the frequency of vibration. And we're going to change the frequency of vibration uniformly. Start with 11 hertz and just move smoothly up. And as this diaphragm is shaking up and down, this ring that's attached here at this post is going to vibrate up and down at the frequency that we set in. And you'll see that there are certain frequencies Okay, there's one standing wave that's going back and forth between these two modes. Now, and then keeps going up, and then it goes away. And now there's other standing waves patterns there. Again, you're just moving uniformly in frequency, and you get different patterns. And when you're between the resonant frequencies, nothing. Okay, where does light come in? Light being a photon. Well, if only certain orbits, certain energies are possible, then that means that if I make a transition from one to the other, I have to either absorb energy or give off energy, and if it's in the form of light, it has to be in a certain packet, a certain bundle. It's not a continuous wave with all frequencies. So here we go from one outer orbit to an inner one, and we get a frequency of light this way. We go from here to here, a different frequency of light. From here to here, a different frequency of light again. So when you look at the light that's coming off of this atom, and you go through a prism, and you look, you don't get a continuous spectrum of light, like a rainbow. What you actually see is particular wavelengths corresponding to these lines. This was known a good 20 years before the very first inklings of quantum mechanics were developed, that light was coming off of atoms with particular wavelengths. Every atom had its own particular set of wavelengths. Every sodium atom looks the same, but they look different from other atoms. So each atom has its own fingerprint that you can identify. And this is what chemists make use of to identify the chemical composition of a molecule. You see hydrogen. Here's sodium, which a lot with more lines in the yellow. You know, sodium streetlights have a yellow tinge. And if you put some salt, sodium chloride, onto a candle, you'll see some yellow in the flame. Here's helium. Helium, so it's got lines that look like hydrogen, but it's got lines that are different than hydrogen. They saw this from light coming from the sun, and they knew that it had to be a different element. It was an element that at that time had never been found on Earth, so they thought it was an element that only existed inside stars, so it was called helium after Helios, the sun god, right? And for a long time, they didn't know that helium existed on Earth. So like at the Macy's Thanksgiving Day Parade, they used to just drag these deflated balloons down Broadway. It was a rather pointless exercise. Neon signs tend to be reddish. So every atom has its own set of wavelengths. And to show that you could see this resonant emission and then resonant absorption, we have another demo here. Here are two tuning forks. And this tuning fork is different from this one, has a different frequency, but we've added masses to it so that it will have the same frequency as this one. We're going to strike this one. These are hollow wooden boxes that are in contact with each other, so any vibrations generated by one tuning fork can be sent over to the other. We'll see that when they're resonant, now we're going to move the mass just a little bit, but it changes the resonant frequency of that tuning fork. And there's no resonant absorption. So we have this picture of an atom with these standing wave orbits, the transitions of light that could be the emission of light due to transitions between these orbits. It is so simple and elegant that it's really a pity that it's absolutely wrong. It is not right at all. This is not actually what the Schrödinger equation says. The Schrödinger equation says that instead of this type of a picture, which everyone always, this is the universal symbol for an atom, right? Exactly 3 orbits that are at angles, these angles to each other. This is the actual picture of an atom, is clouds of probability. That there is the nucleus, and then basically the Schrödinger equation says, it tells you, if you solve for this Greek letter psi and you do something mathematical to it, it tells you the probability of finding the electron at some point in space and time. And if you do this for a 3-dimensional atom, where there's an electrical interaction between the nucleus and the electron, but of course there's an attraction, but there's also a repulsion of the electrons with each other, and you solve for that, and it's a very complicated problem that people used to do the hard way until they went ahead and invented computers using quantum mechanics. what you find is that only at certain distances and only for certain angular momentum, certain energies of the electron, are the electrons allowed to be where they are. So when you solve this for an atom, what you get is basically a set of possible places the electron can be. So it's having, instead of this auditorium, you're going to have an empty room with a set of chairs. Actually, and I'll explain in a second, they're not chairs, they're love seats. I'll explain. Right? And you have, and the Schrodinger equation says that there's closest to the nucleus, there's one chair, then another chair, then 3 chairs, then another chair, 3 chairs, 1 chair, 5 chairs, 3 chairs, and so on. And that exists whether the atom has 1 electron or 100 electrons. Different atoms have different locations of the chairs. That's not really important right now. So, if I have hydrogen, now I'm going to turn these into love seats. If I have hydrogen, hydrogen is 1 proton and 1 electron. Electrons want to be in the lowest energy, so they'll go closest to the nucleus, so that's there. But there's all these other possible chairs, and so you could have transitions up to here, or from here, or they can go down. And when you do a calculation of where those chairs are and the energy spacing, it agrees exactly with the observed spectrum of lines. So this gives great credence to this approach. Okay? Now, what if I have something that's even more complicated, like 2 electrons? This is when I need to finally use that third bit about spin. Okay? Everything, light and matter, has an intrinsic rotation, which can be described as an intrinsic magnetic field. If electrons have an intrinsic spin, then when the 2 electrons are near each other, they interact. And they interact through those magnetic fields, through that spin. So, what's easier to have 2 magnets where they're both pointing in the same direction so they can kind of repel each other, or where the South Pole is close to the North Pole and the North Pole is close to the South Pole? That's easier. That's the way they like to be. 1 going up, 1 going down. So when I have 1 clockwise, 1 counterclockwise, right? Helium, that's helium, right there. Right? This is called the Pauli exclusion principle. What if I have something even more complicated? 3 electrons. Well, there's only clockwise or counterclockwise. There's no other wise. There's no other way for me to get that into the love seat. It's called the Pauli exclusion principle, not the Pauli togetherness principle, the kumbaya principle. No. So, lithium, with 3 electrons, has to have an electron up there, like that. Okay? Carbon, 6 electrons. Aluminum, 13 electrons. And this is now, we start to understand chemistry. We start to understand why there are certain patterns that you can put in the periodic table of the elements. This is why it's periodic, because certain patterns repeat because of the way the chairs are laid out. These electrons, once they're paired up and sitting in these chairs, they are happy as clams. I have no idea why clams are happy. But apparently, they are like the gold standard, the Cadillac of happiness. So they are, and so they don't do anything. X-ray spectroscopy, blah, blah, blah. But anyway, they don't do anything from what we're interested in. So these are called the core electrons. All the action, all the chemistry, all the semiconductor solid-state physics is going to happen in this last row. Now, 1 atom is good. But if I want to have something like, I don't know, anything, I need to have something that's got, and the average material has on the order of 1 trillion atoms per cubic centimeter. A little bit less, but that's a good round number. Per cubic inch, definitely a trillion. That's a lot of atoms. Now, you take all of them, and again, I'm going to ignore these guys. I'm just going to focus on this, but don't forget that there's a whole set of empty love seats above it that are not doing anything. They're just sitting there, but they're possible. They're possible places to go. So what happens is this guy here, this could take two, and each atom of the trillion aluminum atoms has the possibility of having 2 electrons, but only 1 electron is there. So that means that for aluminum, you have a room now, not with 1 chair, you have a giant orchestra, a giant auditorium. And there are a trillion seats, and each seat is a love seat that can take 2, but each love seat only has 1 electron. So that only the first half of the auditorium is filled. This is called a metal. Or there are certain elements where the last seat is doubly occupied. That means that the orchestra is completely filled, every seat maximally occupied. That's called an insulator. Now, there are upper seats that are not doing anything, and in a metal, we don't really care about them at all, but they do play a big role in insulators. You could think about this as a balcony that has exactly the same, but did you know that there's a balcony above this auditorium? No, because there isn't. But if there were, you wouldn't be accessible to it because you need some energy to get up to the balcony. This is, by the way, this is why we call these insulators if the gap between the orchestra and the balcony is large compared to what? Large compared to, say, visible light. Have you ever stared out the window and wondered, how come I'm able to look through a window? You're able to look through a window because it's an insulator, doesn't conduct electricity, and the gap between the orchestra and the balcony is in the ultraviolet. We don't see the ultraviolet. We see the visible. Visible has smaller energy. Visible has an energy that would go from here to here. But there's no seat there, so the electron can't go there because there's no place for it to go. Quantum mechanics says if psi squared is 0, that means the probability of finding it there is 0. So you can look. Now, if I want to change the color of glass, I put a chemical element in it. Vanadium, selenium, chromium. And we call that stained glass. That puts a seat right there. So certain colors can be absorbed and emitted. So that's how you make stained glass. We're going to get back to this in a sec, because pretty soon we're going to make a laser out of that. Or if the gap is small compared to visible light, or that room temperature heat is enough to get some electrons up into the balcony, that's called a semiconductor. If we put some electrons up there, now if I try to push them with a voltage, well, these guys can go to the other spaces. Now there's empty seats. Before there weren't. And now these guys want to go up here, which is another way of saying that the empty seats move down. So I have both electrons and holes. Electrons that have negative charge, holes act like positive electrons. P-type, N-type, P-type. This is a semiconductor. It's true also in insulators, but the insulators, the gap is so large that you never really see this. Now I'm going to take this metaphor and just strangle it to death. Let's say I add another element. Say I have a material that is normally an insulator, and I put some other element in there, some phosphorus atoms, and they produce seats, not up in the balcony, not down in the orchestra, but somewhere in between, which I call the mezzanine. If I give some energy and excite an electron, it will go up to the mezzanine because it's available rather than going up to the balcony, which takes more energy, okay? Now, if I say, see here, normally there may not be any electrons in the mezzanine, but if I send light in, some could be actually excited up to the balcony, and then they'd fall down into the mezzanine, and they'd stay there. I turn the light off, and eventually there's empty seats in the orchestra, and they drop down. When they drop down, they give off some light. This produces what at one point in my life I thought was the coolest, most amazing technology possible. Glow-in-the-dark toys. Right? This is how you shine light on the glow-in-the-dark toy, you charge it up, you're putting electrons in the mezzanine, you turn the light off, and then it glows because those electrons fall down, emitting light. Eventually, it dies off, and you have to recharge it again because you run out of electrons in the mezzanine. So one way to get the electrons out of the mezzanine is to let them fall on their own. Another way to do it is to push them, to induce one of them to fall, and as it falls, it jostles the next one, which jostles the next one, and jostles the next one. So you send in one photon, and it falls, but then it triggers the next one, and triggers the next one, and triggers the next one. And this process happens like at the speed of light, so you don't notice any time delay. So you send one photon in, and you get many photons out. This is described technically as the light amplification by the stimulated emission of radiation, or a laser. So this is the laser, and we only understand it, we can only design this with an understanding of these states in these seats and what the electrons are doing and what the light, which are bundles of energy, are doing. Okay? And there's practical applications for that, of course, as well. So, that's lasers. The other thing I promised you is to tell you about transistors. So I have to tell you about semiconductors. A semiconductor is an insulator with a small gap that may be visible light, infrared light, room temperature heat is enough to get some electrons, not all, but some, up into the balcony. But if that's all you're interested in, get a metal. What you could do with a semiconductor is you could take another, say silicon is a semiconductor. I put phosphorus atoms in. The phosphorus atoms each have an electron. They have a row of seats that's right below the balcony. That gap is very small, so at room temperature, boom, these guys love to go up into the balcony. It's real easy. They don't have to go from here to here. They just have to go this small little jump, right? It's just a hop for them. Or I could put seats in a material with boron in silicon, and they have empty seats, so that means that these electrons could easily hop up into them, which leaves a row of missing electrons. This would be called N-type because these electrons are negative. This would be called P-type. And again, if that's all I wanted to do by adding, and actually it's not a big thing, you add 1 part per million of phosphorus or boron, and you can change the ability of the silicon to conduct electricity by thousands and thousands and hundreds of thousands of times. But again, if I just want to make something conductive, there's something called copper. I could just use that. What the benefit here is, if I have an N-type material and a P-type material, and I do something complicated like this, and put them next to each other, now I've got the technology that our society is based on. I have a P-type material and an N-type material, and at that barrier is what's called a P-N junction. All that I've done is I just take these two, and these electrons over here fell into the empty seats that were over here. And what happens is, by putting these two next to each other, I uncover electrical charges that are here, and electrical charges that are here. So suddenly, without attaching a battery, there is now a voltage at that barrier. There is a voltage at that barrier because I had charges, the negative charges in the positive charges in the N-type material were covered up by the electrons. The positive charges from the boron ions were covered up by the holes. The negative charges of the boron ions were covered up by the holes. But once they combine, some of the electrons and holes recombine, and now those charges are uncovered, and they create a voltage. And if I have a voltage, I can move a current. If I have a voltage, that means that it's easy for electrons to go in one direction if they're going with the voltage, and it's hard to go in the other direction. So that's called a diode. And so here we have a clip-hip. Someone asks, I'll explain why he's called that. And showing that going from the N-type layer to the P-type layer, it's hard work to push the electrons against that voltage. But if you go with the voltage, it's very easy. That's good, but it gets better. Because if I shine light in, and if the light is absorbed, creates electrons and holes. The electrons move due to this voltage. The holes go in the opposite direction, and I get a current out. So I have a solar cell. I shine light on it, and because there's a voltage, not connected to a battery, the voltage is inside the thing, no moving parts, I get a current out. Or if I force a current against, I have to do work on this, I force a current against that voltage, then when the electrons and holes are above each other, they drop down and they get light out. That's a light-emitting diode. So the p-n junction is a one-way door that allows current to go in one way but not the other. You shine light on it, you have a solar cell. So you shine light in, current out, a solar cell, or current in, light out, an LED. That is just understanding semiconductor, understanding the chemistry, understanding the quantum mechanics led to this. And we're nearly there. Oh, I have one more demo. What did I do? There. Okay. One more demo. You can make a feather rotate. But again, you're not connecting it up to any battery or any power supply. You're using sunlight. By the way, enough sunlight falls on the Earth in one day to meet the electrical needs of the entire planet in a year. If we had solar cells 10 miles by 10 miles, 100 square miles, it would supply all the electrical needs of the United States. Now, you want to put it someplace sunny, and we don't all live in Arizona. Shock to the people in Minnesota. But you'd like to have some way to get that current there without any loss. One last bit that you can do with these p-n junctions, I have an N and a P, and I could put another N. And now I've made a transistor. There's a barrier. Now, no matter which direction I try to push a current, it can't go. You go, okay, great, that's brilliant. Why did you do that? I did that because if I attach a wire to this middle layer and I apply a small voltage, I can decrease that barrier dramatically. So now it's very easy for a current to flow in either direction. If I have a high current, I'll call that a 1. If I have no current, I'll call that a 0. And now I'm keeping tabs of zeros and ones using this transistor. Used to be that to do this, you used a vacuum tube. And this was the analog of a transistor. This is actually what the transistor was meant to replace. By the way, at Bell Labs, where they invented the transistor, in one of the conference rooms, I saw a sign that says, "You do not invent the transistor by trying to perfect the vacuum tube." This is the first integrated circuit, which is like 3 vacuum tubes and some mercury relays. The first semiconductor transistor and vacuum tube did not look that much better. This is the very first. It is a triangle of germanium that's about a centimeter. It's about the size of your fingernail. And this is also about like the size. This is a microscope slide. This is the first integrated circuit. But if all you but once you got that, you can get this. Because if a transistor is going from an N to a P to an N, and if that's all I care about, if I define a sandwich, a jelly sandwich, as bread and jelly and bread, and as long as you have that, you have a sandwich, then I don't need a big piece of bread. I can make that as small as I want. And as long as I have bread to go to jelly, to go to bread, I've got a sandwich. So we started with the transistor in the 1950s that was the size of your thumbnail. And now they are the size of a cell in your thumbnail. Some of them are as small as viruses. That's not all that we can do. A colleague of mine that I collaborate with and work with a great deal, Uwe Kortsagen, in the Department of Mechanical Engineering, is an expert in making nanocrystals. And he can make silicon nanocrystals extremely small. A nanometer is 3 atoms end to end is roughly a nanometer. So if you're making nanocrystals, you're making things that are really very small. If you have a radius of 1 nanometer, you have only 200 atoms in that sphere, and 140 of them are on the surface. But when you get things that small, the electrons know that they're inside a box. And so each vial here contains silicon nanocrystals in a suspension. When you shine ultraviolet light on it, the silicon glows. If the nanocrystals are big, they glow red. As you make the nanocrystals smaller and smaller, they grow yellow, green, orange, yellow, green, purple, blue. They're all the same chemical. It's all silicon. All you've done is change the size of the crystal. Now you have a new knob to control matter. If I wanted to change the color of the window, I had to put other chemicals inside the window. Now we can change the properties by changing the geometry. It gives us another thing to change and to control. Uwe, of course, doesn't do this on his own. He has a photo of his group here, where you can see, this is why I've worked with this guy for 20 years. That's Uwe right there. Working with Wivell, we've built a system where we can make nanocrystals and then inject them into another system that grows other semiconductors and put the nanocrystals in like little chocolate chips. This is a high-resolution TEM image of a disordered material, so the atoms are random. Each one of these white dots is a silicon atom. And you can see there's actually a crystal imperfection in this small little nanocrystal here. And what you get is you get materials that don't have the properties of the host material, don't have the properties of the crystal. They have something, they show behaviors that we haven't seen before. And we've been doing this for 20 years, and we haven't begun to fully scratch all the surfaces that are there. And so when you hear people talk about nanotechnology, this is what they're talking about. This is about transistors that are the size of viruses, that when you get that small, the geometry, new phenomena show up. And that is what people are working on now. So, in summary, 100 years ago, scientists were trying to understand how atoms behaved and how they interacted with light. They found that they had to create a new branch of physics called quantum mechanics. This in turn led to the development of solid-state physics that basically changed the world we lived in. You could have powerful computers with vacuum tubes, and to have a computer that's as powerful as this laptop, it would probably be the size of this auditorium. If that's the size of computers, not everyone has one in their house. There's no reason to connect them all on a World Wide Web. You don't have Wi-Fi, you don't have the internet. You might have an internet of those few computers talking to each other, but that's about it. So the things that we take for granted really only come about. And again, people were trying to just understand atoms and how they interact with light. And 100 years later, this is where we are. So, what's next? Next week, we'll hear about superconductors. Superconductors are materials that can carry current, thanks to quantum mechanics, with no electrical resistance at all. We don't know how to make them at room temperature, but if we did, we'd put those solar cells out in Arizona, and you could bring the current with no loss all the way to Minnesota. Not only that, they hate magnetic fields. You take a superconductor and you put it above a magnet, and it hates the magnetic field so much that it creates its own magnetic field to push it away, and it will levitate. He'll tell you all about this next week. I want to thank you all very much for your attention, and I have one last gift for you all, and I mean a gift. I want to thank you all for coming to this inaugural talk. I want to thank you for coming out on a rainy day, right? It was raining real hard around like 5 o'clock, and you're looking out saying, do we really want to go and listen to this, right? But you're here, and I appreciate this. So the dean's office called me up, and they said, we were cleaning out this classroom, and somebody left behind these copies of Richard Feynman's The Pleasure of Finding Things Out. So I have 3 copies of this book. One, two, come on, here we go. I have 3 copies of this book. Look underneath your seat. If you see a poster for Quirky Quantum Mechanics, now maybe you're not sitting there, so maybe it has to be a seat that's next to yours. Who's got the Wonka tickets? Oh, there's a Wonka ticket. Another Wonka ticket. There's one more, and a third. There we go. Come on up and get your books. There you go. Oh, thanks. Great, thank you. Congratulations. Well done.
I was not sitting in that seat, but...
That's okay. Did you kick anyone out of the chair?
No,
oh, okay. Then it's okay. Then it's okay. The Pauli exclusion principle at work. And with that, I want to thank you all very much.